trying to wrap your head around quantum mechanics when all you've got is classical logic, well, it's like,
Trying to nail jelly to a wall, maybe?
exactly. It's just particles in multiple states, uncertainty everywhere you look.
Enough to give anyone a headache.
Totally. But the good news is there are folks out there trying to bridge that gap.
Oh, yeah. Like who?
Well, in this deep dive, we're checking out this paper by Jesse Werbo. He's using something called quantum contextual topos, QCT for short.
QCT, huh? Sounds intriguing. What's the deal with this Werbo? What's he trying to do?
Well, it's interesting he's not shying away from the weird stuff. Like, not at all. Embraces it, actually. Trying to figure out, I don't know, how logic itself even works in the quantum world,
I'm picking up what you're putting down. It's like our brains, they crave order. They want things to be nice, predictable.
Right. And then quantum mechanics comes along, throws that all out the window.
Exactly. It's not even just that it's like strange. It's that the tools we normally use to understand things, our classical logic, they just kind of fall apart at the quantum level.
Yeah, and Werbo, he just goes right for it. He talks about this thing called non-distributivity.
Non-distributivity. Okay, now we're getting into the weeds a bit.
I know. But it's cool. Basically, it means that the order you do things in the quantum world, it can change the outcome. It's wild.
Whoa, really? So, like, what stirring your coffee before you add sugar gives you a different drink than adding sugar than stirring?
That's a really good way to think about it, actually. Like, in our normal world, those are the same, right? But in the quantum world, that order matters a lot.
That's pretty wild. I mean, I kind of get it, but also, what are the real implications here?
Well, that's where Werbo brings in this example of a particle and its momentum and position, like that whole uncertainty principle thing.
Ah, classic physics thought experiment. Can't know both at the same time. Got it.
Right. But the thing is, in classical logic, you can talk about those things in any order, right? Position first, then momentum, or flip it around, doesn't matter. The statements are still true. But with quantum mechanics,
Gets all messed up.
totally. The order you put those statements in can actually change the system you're describing. It's like, whoa.
So it's not just that quantum mechanics is weird, it's that logic itself has to change if we want to even try to get it.
You got it. And that is where QCT comes in, my friend. New rules for a new game.
Yeah.
New logic for a whole new world.
Okay, you've officially piqued my curiosity. This QCT thing. Tell me more. So imagine this, right? What if, instead of just like talking about quantum stuff, we could build a map of it?
A map, huh? Oh.
Yeah, but like a special map,
Yeah.
where different parts of the map, they have different logic rules, different contexts for how things actually work down there.
Okay, I'm kind of with you. A map of quantum logic, basically. But, like, how do you even start to make a map of something that weird? It's like trying to map a dream or something.
That's where this gets really cool. See, Werbo uses this thing called stone spaces.
Stone spaces. Catchy. What are this, some kind of Zen garden for particles?
Not quite, though I kind of like that image. But, okay, so basically think of them like a special kind of map, right? But instead of showing you streets and stuff, they show you abstract mathematical structures.
So instead of like, where's the library, it's like, where's the non-distributivity zone?
Yeah, exactly. Like you can plot out all these different quantum contexts, see how they all fit together, maybe even find some patterns.
Okay, so it's like bringing some order to the chaos a little bit.
Bingo. And the really cool thing is these stone spaces, they're not just something Werbo made up. They're connected to the structure of logic itself. That's where this duality thing comes in.
Duality. Man, we are really going deep down the rabbit hole now.
I know, right? It sounds kind of intimidating, but it's actually pretty neat. See, there's this thing called Stone's representation theorem, long name, I know. But basically it says you can look at the same thing in two different ways, like abstract math on one hand, and then like a real space on the other.
Two sides of the same coin.
Exactly. And they're totally connected. It's
Yeah.
like you can think about quantum logic in terms of equations, right?
Yeah, makes sense.
But you can also visualize it like as an actual space, a landscape with all these different regions, each one with its own set of rules.
Okay, now my mind is officially starting to bend a little. So, like, what does this duality thing actually do for us? How does it help us make sense of all the quantum weirdness?
It tells us that there's a bigger picture, a deeper structure behind all the craziness. And these stone spaces, they let us map it out.
So we're not just lost in the quantum woods anymore. We've got a compass and a map.
Exactly. We can see how different quantum contexts connect to each other and maybe even start to figure out how things are going to behave.
Okay, I gotta say, this is pretty darn cool. But how do we know this whole stone spaces thing actually works? Like, it's not just some nice idea someone had, right?
You're right. You've got to test it. And that's
Yeah.
where Werbo goes all out. He proves it. And the proof, it relies on this thing called the double duel.
The double duel. All right, you're gonna have to hold on a sec. What in the world is a double duel?
Duel.
Sounds kind of like looking into one of those mirrors that goes on forever, you know?
Huh. Not a bad analogy. It's all about taking a concept, reflecting it back on itself, a way of making sure our logic holds up. Like, are we even making sense here? It's a check.
So we're taking this QCT, this map, and we're basically putting it through the ringer. Stress test.
Exactly. Making sure it doesn't crumble. And, get this, Werbo proves that QCT passes the test. It works.
Okay, so it's not just a cool idea, it's some serious math behind it. That's huge.
Huge. It means we're onto something real here, not just, like, abstract theory. This math, it lines up with how quantum stuff actually behaves.
Okay, so big picture time. This means we could be looking at a whole new way of approaching things like quantum computing.
Oh, absolutely. And it goes even deeper than that even. Remember those stone spaces, the maps? They aren't just static pictures, they actually preserve the logical relationships between those different quantum contexts.
So it's like a map that doesn't just show you where things are, but how to get from one thing to another, all while following the rules of quantum mechanics.
You got it. We're talking about navigating the quantum world on its own terms.
Wow. So not just describing it, but actually using it.
That's the hope. That's why this research is so exciting. We could be on the verge of unlocking some really wild stuff here.
From the totally bizarre to the incredibly powerful. Well, folks, there you have. This deep dive's taken us from mind-bending weirdness all the way to some seriously elegant math.
And you know, the thing about exploring the quantum world, it might just make us rethink how we understand, well, everything. Who knows what we'll find out there? What other rules we might have to rewrite?
It's a whole universe of possibilities. Thanks for exploring with us.